Listen, is it working right now?
Yep, I can hear you now.
What a relief. That's great. Then you can link back and forth. Things will be recorded anyway. So if you do not listen to me now, it's okay. So those who are not registered for the class, but coming here for auditing are also invited to make presentation next Friday. So there are 8 registered and 1 audit, and there are 9 subjects to present. And those will be very brief for me as presentations. So here we are in the physical chemistry course. Wavy nature of electron is like more narrow area of quantum theory. And at the edge between 19th and 20th century, the whole humankind was browsing in the dark, not able to get the logic because it is all counterintuitive. And this theory that is able to describe properties of electrons cannot be built on the building blocks of all previous science. So it needed some additional statements that were not available. And one needed to design something like go nowhere, find something that you never saw. And it was like debates, arguing for a long time, and then just big company of scientists agreed to introduce new area of science into the community, but add like so-called postulates, the statements that we just agree to accept as something that doesn't need to be proved. And it was more philosophical, because without this additional fundamental background, it is not possible to predict or interpret results of experiments correctly. And this so-called postulates are very popular and famous part of any textbook. They are reflected well in the Wikipedia, and I'm going to show summary of these postulates on about 1 or 2 pages and ask chop them between class attendees, prepare like 4-minute slides and present next Friday. Is it possible? And so that there will be no confusion, today we will vote who wants which of the postulates. So during the class or by the end of the class, we will have it installed. We will do it. And those who are not attending neither Zoom nor in class will be just assigned. So this is thing number 1. And all our efforts until today were targeted to avoid too much confusion, to bring the actual science that will start after we learn postulates with a little bit connection to our everyday common sense, because otherwise it looks very scary. Like if one wants to start this quantum theory in a rigorous manner, one can do it only with heavy math, which scares people as well. And if you do some connections and parallels with other areas of science, it is a little easier to get through. And when we go into more practical things, it will be easier. I hope so. So this will be the first part. The second part will be to take one derivative. So basically, we came here to take a derivative. And before I go to this boring slides, let me just tell so that we all agree what is going on, and even if we skip some details, everyone feel happy. Last time when we met in class was evolution operator that helps us to go from past to the future. If you have wave function, and we didn't define wave function yet rigorously, but if you have it for the past, we apply evolution operator to it, then we can get wave function for the future. And philosophically, one needs nothing else, but practically it's very uncomfortable. So today we are going to take derivative of the evolution operator over time, assuming that we project from past to the future on a very short interval. And then by taking, you remember this evolution operator has exponential, and everything is set up in positive sense. By taking derivative of exponential, one gets exponential back, right? Plus, not plus, times the things that were in front of independent variable. And by applying this trick, we will be able to cancel exponential and make an equation that will connect past and future with only this operator of total energy. And by this operation, we will get the main equation for the rest of the semester, so-called Schrodinger equation. So this is quite simple. I have several slides with ugly calligraphy, so to say, but is it reasonable? Do you agree about the derivative removes exponential and makes things simple, right? No one objects. So the rest will be technical details. So here is that slide. Where these postulates are like copy pasted from one of the textbooks, and you're welcome to take this one as an example, or look online, or any textbook. They're the same. They just expressed in slightly different way, and some people even number them a little bit differently. But I believe it is a really great exercise because it's more philosophical expression of the thoughts rather than math, and I think everyone will be able to communicate. So I skip going over them. Here is the equation that we are going to derive today, and you see there are no exponentials. We will just get it by applying time derivative to the evolution operator. And here is the list of class attendees, including the one who is auditing. And here are the postulates that were on the previous slide, and plus I made up a couple of additional subjects which are closely related, like refresh some linear algebra, which we will need for sure, like eigenvalues of a matrix, and connection between evolution operator and Schrodinger equation, basically what we will be doing today. So I have wrapped this slide as a standalone Google Slides document, and let me try to open it and make sure that okay. So, oh, I see some of you already got an idea what to do. So you can log in and connect your, either type in your name near the postulate that you like, or if you do not feel comfortable typing, one can just select line and connect. I'm just giving an example. Like, connect your name and the postulate. Yes, selecting most preferred option and least preferred option is fine. So before we depart, I'm going to have a glance on it once again, and if there will be missing spots, I will ask those who didn't feel to just verbalize it by word, or if you do not have your laptop with you. So if someone wants to shout out loud which subject you like, you can do it right now, or we can wait until the.
I'll just take a random one at the end, probably.
Okay.
Yeah.
The number 9 will be, I would select number 9 because I have already prepared today's lecture and I know the subject, and it will be related to the research project that we all will do. Okay, so one could call our class history of, instead of physical chemistry, you can call it history of Nobel Prize awards in physics. So all things that we are going to over were awarded with like prizes at the first half of the 20th century, and we already covered the in one sources he called Prince de Broglie, in other Duke de Broglie, but we already covered that like, electron is a wave, right? This is an experiment that deals with quantization of vibrations. So vibrations are not just point charges changing their direction, but there are also wave functions related to distribution of positions between atoms. And Raman didn't spend much time explaining. He just found experimental evidence where this is seen. So these two guys, Heisenberg and Schrodinger, they were in good relations, but in some sense they were competitive. So they offered two alternative mathematical implementation of the ideas behind quantum theory, and majority of the world is following Schrodinger, but the mathematical tools invented and offered by Heisenberg are equivalent. They produce the same results. They're just a little less comfortable for non-mathematician. So the Schrodinger approach that we are studying basically today deals with these wave functions, which are continually distributed functions that we all are dealing in calculus, right? And they are easy to plot, they're easy to visualize, and therefore community like them it more. Heisenberg, we will also cover his theory a little bit during the class, but instead of plotting nice wave functions, he dealt with matrices, like order matrices and no visualization. So each procedure, each thing that happens in the world is just a matrix. And it's very boring and dry, although sometimes it is efficient. And we'll go over it, but they both were awarded. And about 15 or 18 years after I completed my degree, I suddenly realized if I look the pedigree of advisor of advisor of advisor, this line brings me to this guy. I never knew when I was studying. And we will also have the connection to Dirac. He invented advanced equations that we do not need right now. But in addition to equations, he invented a notation that brings peace and friendship between these two. He brought a notation that combines wave functions and matrices into one general mathematical object. And it looks scary and boring right now, but later on it will, if you want to look smart in front of the audience, you can tell, I'm using direct notation. Oh, impressive. So there is no time to read right now, but if you have some curiosity, I recommend reading this couple of paragraphs, and you will see connections with what we discussed in the class. So in the actual things that people are deriving, solving, and publishing in scientific papers, you will not see the intentions and original brilliant ideas that drive people to do things. But in the prefaces to books, sometimes the people disclose what drove them, what drove their minds. And if you look through the preface to the book written by Schrodinger, who designed his equation, he explains the train of his thought, which is not part of actual work. In the work, he just makes boring, dry derivations. And in the preface, he tells approximately same things as we did in our previous lectures, like connection to the path, accumulation of action, and if you find time to read, you may enjoy it, and it will cover the gap between everything before quantum and quantum world in the non-mathematical way. Okay. So last time we were planning to go over 4 equations and we finished on number 3, right? So the only thing we need to complete today in the remaining 24 minutes is to jump from this equation to this one. And basically, we are going to apply derivative over time and see what happens. And errors are chasing me. It should be the same symbol on the left and right. So we are going to go from equation from the 3rd line to the 4th. And I claim that by applying derivative, you will get this one. So this is what we agreed last time in the class, that one can go from past to the future by training with several values of total energy by time interval. Right? And the evolution operator can be just presented as one symbol. So we have wave function of the past, wave function of the future, and factorized multiplied by evolution operator that connect them. So we are going to make a mathematical experiment. We are going to apply the time derivative to left and right part. So what do we see on the right part? How many factors are there? 2, right? And each of them may eventually depend on independent variable. So if these 2 factors are depending on independent variable, how do you call this rule from calculus? Just differentiation of product, right? So derivative of the first thing times second unchanged plus first thing unchanged times derivative of the second, right? Okay. And if we do not have enough power and might to change the past, which is kind of nature in common sense, then the past doesn't depend on our time evolution, right? Then the second term can be dropped because derivative of the wave function of the past over time that is in the past will be 0. So in fact, we will be doing only derivative of the evolution operator. it is so ugly. I prefer probably just writing it over. I don't guarantee that it will be better, but it's easier to write than to read. So we will have exponential minus y over h bar integral t prime t prime from, let's start our history at 0 and go into time t. And it will be our initial function. And this will be our final. So if we apply derivative to the evolution operator, we are going to get two things. So we will reproduce the exponential as it was without changes. So the derivative of exponential is exponential. Probably use the black ink once again. And second part will be time derivative of this stuff in the power of exponential. D dt minus h bar integral h t prime. So by taking this integral, the constant will go up front without any change. Minus I h bar. And then what is the derivative of the integral?
It's just a function.
Okay. So and then I return to the black ink. E h bar integral h dt prime. And then we put equals, and here we need to keep our psi initial. So anyone finds any errors, or you okay with this value? Now let's look on the psi initial and this leftover of the differentiation. How do we interpret it? This is only the one non-trivial thing in the whole today's meeting. And it is easy. It's not a trap. Just let's make connection. So this is initial wave function. And this thing is equivalent to our original evolution operator, right? So by applying evolution operator to initial wave function, we will get wave function of the future, right? So if I put this stuff in the box, then it will be equal to wave function of x and t, final wave function. And here I did forget one thing. So we applied derivative to the left. We need to apply derivative both to the left and to the right. And then time derivative of the final, of the wave function of the future is equal to this combination of constants times this capital H, which is operator of total energy, times what? Wave function of the future. So time derivative of the future equals future multiplied by Hamiltonian, right? So let me summarize it maybe in this little order. So ddt of the psi final xt equals psi final xt multiplied by minus I h bar capital H, total energy operator. So if you're taking notes and you want to have your notes very brief, maybe it is the only thing that you need to write down. This is a like fundamental for everything we do from now on. It looks like all my goals are done. I was boring and feeling sorry that they came later, but I think my main goals are fulfilled for today. I'll probably have more slides to show, but this is the main thing. And I want to brag a little bit. In most of my colleagues who offer undergraduate physics, chemistry, and physical chemistry, and quantum mechanics just introduced this equation from the beginning. And I don't know if was it good or bad, but we kind of derived it. We set it from the intuitive expectations. And looking back, most of the things we speak up in the class will be forgotten. I'm not nourishing expectations that each of my work will be carefully processed to the rest of the life, but at least I hope that you will carry the feelings that it is not coming from nowhere. It's not postulated. There are logical ways to bring this equation, to set it up just based on thinking and analysis of situation and playing with hypothetical things. This step from challenging situation when nothing can help to this equation that will address basically anything that happens in chemistry was like a challenge for humankind, and there were no way to solve it. It was like browsing in the dusk, offering realistic and unrealistic hypotheses, and coming to it makes all of us on the rails of productive research. Okay. I think it should be the same, just I am very sympathetic to anyone who tries to do it right. It's basically the same thing, but again and again. Oh, okay. This one is better, but we already did it. It's maybe once again, so evolution operator wave function, derivative of evolution operator times wave functions plus evolution operator of the derivative of wave function. If we drop the term here and the evolution, if our t is very small, then instead of integral, we can just have a product, right? And it is just a little easier to take derivative of the product than the integral, although the result will be the same. So taking derivative, we have the exponential and this minus I h bar and Hamiltonian operator. And then this derivative of evolution operator is plugged into this attempt to derive to apply derivative to the wave function. Okay. Okay, so another little ugly writing, but I think you wouldn't mind. So the Schrodinger equation is an excellent tool to those who are in sense of the calculus. So this Schrodinger equation is example of differential equations in partial derivatives. The Hamiltonian operator includes derivatives over space on the right part, and on the left there is a derivative over time. And if you took differential equations and you apply your skills, then it can be solved by applying this equation to most of the chemical systems. If we go over an alternative path, if we do not like deriving equations, or if you just don't have time, or if it's not our major goal in the life, we want some either people assist us or computers to assist us. So for computational solution of the Schrodinger equation, this calculus form or derivatives is not ideal. There are better ways suited for solving computation. And again, this equation helps us to go forward in time, projecting past into the future. So let's look on the derivative over time. The derivative over time can be opened in the same way as we were making definition of derivative in calculus, right? So the function in the future minus function in the past, just carry the minus to hold it, divided by increment of the argument, increment of time, right? Josh, you agree? Yeah. Okay. Now, I'm plugging this definition to the left and keeping this stuff on the right. So, future minus past equals the thing that we carry from the Schrodinger equations times delta t, right? So I multiply left and right part by delta t. And then I can transfer this near past from left to the right. If you swap sign and I don't know how to remove this screen share thing. Maybe it will not be seen on the recording. But here is a wave function of the near future, psi of t plus delta t equals psi of t minus I over h bar Hamiltonian iterator, wave function of the near past times delta t, right? So what I can do is, I don't want to do anything. How can I interpret it? On the left, we have future. On the right, we have past 2 times. And actually, past is coming twice. First with factor 1, second with factor minus I h bar h delta t. So I can factorize and put past out of brackets. Right? Then, if I do it, so here we have past, we put it out of brackets. And then here we have future, here we have past, and here is like micro evolution operator or infinitesimal evolution operator on the short time. So in some sense, it is again evolution operator, but now we just made a play with equations. We made transition from evolution operator to Schrodinger, and now we came back. We derived evolution operator from Schrodinger equation. In the calculus, did you have series? Okay, so I was going to ask it as a question, but it will be silly for me because the answer is already written. I can hold it. Like, how do you expand exponential into series? Or do you remember this equation in the lower left corner? Is it like something that you remembering in the middle of the night, something that you never saw, or something that you saw sometimes and barely remember? Okay, so this is one of the equations that are worth of memorization because exponential is a really nice function which is not changed upon integration or differentiation, and it is a way how to reproduce it in polynomial form. So the expansion into the powers, polynomial powers, is needed in case when the argument is close to zero. So if x is as good as zero, just slow division to zero, then like 0.001. Then the second, third, and other powers will be vanishing. And approximately, so when the x is close to zero, the exponential can be approximated as 1 plus x. So it will be just in the vicinity of the y-axis, it will be just crossing and showing as a little straight line slope. Make sense? I think no. You don't feel happy about this? No? Okay. Generally, it's not expected that math would make anyone happy, but this little thing is not bad. I hope you all will be happy in 1 minute. So here is x, here is e to the power x, right? Now, when x equals to 0, e to the power 0 is 1, right? And when x is slightly changing near 0, we can assume that in this limit, it is tangential to a straight line. So e, which means e to the x approximately equals to 1 plus x. Make sense? So this approximation of curvilinear function with linear function is expansion in the series. And if we just drop other terms, it is the way. And if some mathematical operations cannot be done to exponential, most operations can be done to 1 and to x. Now, let's look on this Taylor expansion and apply it to here. So 1 plus small thing, right? So we can interpret this part as little x, and then we can roll back from, we can assume that there will be also plus x squared over 2 and so forth, but in we can take this 1 plus x as e to the power minus I h bar h delta t. So at least if the time increment is small, this 1 minus the thing can be rolled back due to Taylor expansion into exponential. So we completed the circle. We started from evolution operator. By derivative, we converted it into Schrodinger equation. And now by looking onto Schrodinger equation and finding differences, we came back to original form of evolution operator. So now you are masters of evolution operator and Schrodinger equation. Oh, anything else? Commutation. And we are over time. So I have forgotten to introduce it as major thing, but maybe we'll speak about projects on Monday so that your schedule will be not affected. But I'll use maybe a few seconds. When we follow Schrodinger, when we try to solve any practical applications in the future, we will see instances when operators like total energy affects wave function. And here is an important thing that we need to look at before we go to it. So in our regular life, like I have a pen and I have a cell phone, or I have a cell phone and I have a pen, changes nothing. And mathematically, like 2 times 1, 1 times 2 is equivalent. But if you are speaking on the differential operators and functions, wave functions, swapping the order is not as harmless. So one needs to look for some price to swap the order of objects. And before we go to practical things, it's better that we realize this aspect. So one of the examples, if one applies derivative to wave function, or one has wave function and then derivative is after. You see, it's different. And here is an example of how one can work on it. But better example. Let's have derivative and just operator of which is independent function position argument. So derivative over x, and then function. So if I apply rules of derivative, it will be derivative of x times functions plus x over derivative of function, right? And now we can compare the left and right sides. So we can look on it like differential operator times x equals to x times differential operator plus an additional price. Or we can subtract this thing from here, and then it will be ready to if I subtract d dx times x times psi minus x d dx times psi will be equal to psi, right? I didn't lie to you here. So I just placed this thing to the left. And now it's a very last thing. You should go after it. I can symbolically cancel psi and write down this identity d dx times x minus x d dx equals 1. So it's a little crazy, but it assumes that the function stays at the end of each term. But this procedure, swapping order of operator, means commutation. And the math that we will be practicing in the following will refer to rules of commutation. So right now we shouldn't worry much, which should be aware that it's not innocent to swap things in their order. Whew. I'm waiting for the symbol telling, yeah, here example. Yeah. Done. Thank you for your questions. Have a nice weekend. Looking forward to see you on Monday, and I will look onto the Google Docs and see. So first Wyatt, second Ellison. We need someone for third. Fourth Joe. We need someone to the 5. Joe has already voted. 1, 2, 3. Josh selected 7. Ellison was already. We'll okay. Ellison's will then keep her. Okay, so who in class didn't vote? Sibyl?
I guess I'll go with postulate 2.
Which number?
2.
Number 2. Okay, C2. Choice number 1. Please correct me if I'm typing your name wrongly.
CY,
CY.
not C.
Better?
CY, not S.
Thank you. I promise by the end of semester I will learn how to speak and how to write. Nate?
Which one do you think would be easiest?
They were easy. I know which one is hard. So the hard is let's go back. Where I introduced. I think the 2 and 4 are hard. The rest are 2, 4, and 5 are hard. The rest are easy.
I can do 6.
Okay, so it will be Nate, selection number 1. Which one is least adverse to you?
I didn't plan to.
Huh?
I wasn't planning to.
Which one?
I wasn't planning to participate.
But you will enjoy. It is really helpful. Number 9 is just summary of what we did in this lecture. And what else? No one likes 5. So you can select either 5 or 9.
Alright.
5? Okay. So it's your first choice. Okay, I think we're done. I don't want to call you anymore. So looking forward on Monday, and I will send to everyone during the weekend the examples of PowerPoints from previous years, so that. Huh?
Yeah, we're meeting Labor Day on Monday, so we don't have class.
Oh, good. It makes me happy. Yes. Okay. See. Have a nice Labor Day. See you on Wednesday. That's super. And then you will have more. I'll send the presentations from previous years. Of course, we are not assumed to copy paste literally, but you can get inspired and compose your own based on what students in previous years were doing. And you'll see with this help, it's quite easy. It will not take much of your time.